I'm Paul Yassa, Extension Engineer at the University of Nebraska. I'm going to talk about the soil erosion process and some soil properties when we start looking at some aggregate stability and erodibility of the soil. What I have here is a rainfall simulator to demonstrate the water erosion process. Now what I've got is a series of 5 different greenhouse flats here just to do a little demonstration of the erosion process itself. Now I'm saying water erosion in this case. We can have the same processes with wind erosion. And the very first step is going to occur on this plot where we'll really see it. Anytime we have bare, unprotected soil, the force of wind, or in this case, the force of water from this rainfall simulator, can detach soil particles. The detachment, some people call it splash erosion. We'll splash soil particles around, and depending upon the lighting here, we might even see some soil particles splash down here onto the metal. And as we see that splash erosion, we're rearranging the soil surface, but we're not losing soil yet. So enters the second step of the erosion process called transport. I'm going to put on water faster than it can soak into these greenhouse flats. They do have holes in the bottom to drain, but if it can't soak in, it's going to run off. And as it runs off, it can transport those detached soil particles, and we'll see the runoff streaming down on this little metal funnels and down into these jars. Now with wind erosion, we get detachment, we get transport as well. That transport is going to be the dust cloud you've seen blowing along. It can also be, as you walk across a sandy beach in shorts, you feel sand particles being blown against your legs. Those are detached soil particles being transported, and you're walking through the erosion process itself. Now the third step of the erosion process then is deposition. Anytime the water slows down or the wind slows down, it loses the ability to carry the soil particles, and they'll settle out or be deposited. Now my deposition is going to take place right here in these jars. So we'll have detachment, transport, deposition. Now typically that deposition might be a low-lying area in the field where the deposition might even silt in, cover up some crops. It might cross over into the road ditch off a construction site and actually fill waterways, drainage ways. Or it could go as far as our streams, our rivers, our ponds, and deposition takes place in the bottom of those. So again, when you start looking at the erosion process with the detachment, transport, and deposition, we want to look at different ways we can reduce the erosion problem. And what I have here then for demonstration is crop residue management. These are the same soils here. This is strictly a tilled soil, had nothing growing on it this year, so it's almost a dead soil this year. This is the same soil here, and all I did was add about 30% residue cover on top of it. A 30% residue cover, while from that angle it might look like a lot of cover, straight down like a raindrop sees, there's about 2/3 of the soil surface is bare. And so we can detach some soil particles. But research has shown that even a 30% residue cover like this can cut erosion by more than 1/2. Simply because we don't detach the soil particles, they can't be transported away. Now the last one here, it's about a 95% cover. And again, underneath this is the same soil if I had here. It's just that we put a lot of residue on top. So we're going to absorb all the raindrop impact that we can. We'll still have some runoff because I'm going to put on water faster than it can soak into this soil. And so we'll see water coming off here, but without the detached soil particles, that water will be a lot cleaner. Now coming on this side, this soil obviously looks a little darker than this one. This one I said was a tilled soil. It's rather loose, poured it into these greenhouse flats. This one's actually a no-till soil. It's a darker soil, it has better organic matter. But more importantly, it has soil aggregation. The soil particles and PEDs are holding together. Now it is loose and crumbly because I dug it up to put it in here. And in fact, when I dug it up, here's some roots even. Those roots would help anchor the soil. But I wanted to compare bare soil and bare soil. And so this has simply got some PEDs, some soil aggregation because it is a no-till soil versus a tilled soil. The tilled soil doesn't have near the biological life, thus it's a little lighter in color. This one's darker in color, better organic matter, better soil aggregation. The last one here is Mother Nature's way of reducing erosion, a permanent vegetative cover. And this is simply some grass that I dug up. So not only do we have good soil aggregation like we have in the no-till soil, we've got the roots there, we've got the wormhole channels, we've got other things helping hold that soil together, but more importantly, giving us channels that water can infiltrate into the soil. If water infiltrates in, it won't run off. If it won't run off, then we don't transport our soil particles. So when we think about the erosion process, the residue absorbs the raindrop impact to reduce detachment, but the good soil structure or the worm channels and the root channels will help decrease transport because we have less runoff. Now I'm going to start up the rainfall simulator here, and we can watch the rainfall then accumulate in these jars and watch the erosion process itself. Okay, we've started the rainstorm event now. As you can tell, the rain's coming down pretty fast here, but striking the soil surface, it's about as close to natural sized raindrops as you can get. This nozzle was selected for rainfall simulator research back in the early 60s, and it's been used across the world for doing erosion demonstrations and research. Now research, they do this in a full-size field. In fact, the research simulators, rather than one nozzle, they'll typically have 15 or 30 nozzles. They'll look like a merry-go-round and run in a circle. But as you watch this middle plot now, unprotected soil, we can see the raindrop impact is now starting to make the soil surface glisten slightly. It is detaching soil particles. We see a few of them splashing down here on the metal once in a while. It's just sort of rearranging that soil surface. With the residue there on the next two plots, though, we're absorbing some of that raindrop impact, so we're not seeing near as much of the glistening. Our no-till plot here is glistening, but we can see the soil structure is almost holding the particles together. They're not falling apart. Now on our till soil here, we are just starting to run off. And as that runoff is starting to come off there, I'm going to try to direct it on down to the jar so we can collect it. But now those detached soil particles are being transported, and that transport is going to happen right down into that jar. And even with our 30% residue cover, we're starting to get transport into the jar now, but it's a lot cleaner soil. That little bit of residue cover greatly detaches soil particle, or greatly reduces soil particle detachment. And down on the end here, our nearly 100% cover. It's coming off, but again, relatively clean. And as we see the jar starting to fill, we see there's a lot less soil in that 100% residue cover jar. Now the volume of water is about the same in all three jars right now, simply because it is the same soil. The only difference is the residue cover on top. But as the rainstorm goes on, we might see some minor differences there in the accumulation of water in those jars. Coming to the no-till plot, the soil aggregates are melting down a little bit, but we see far fewer soil particles being washed away compared to the tilled soil. The tilled soil, the soil particles just are not being bonded together. They're being washed away a lot faster, filling that jar up faster. Now the runoff in the jar looks darker simply because it is a darker, more organic soil. And for the good comparison down here in the end, our permanent vegetative cover, the grass, yes, we have runoff, but it's almost clear runoff entering these jars. As the jars are filling up, we see the runoff volumes are slightly different, but we definitely see a difference in water quality. Now it's a little hard to tell right now because the soil particles are still in suspension. But if we let the jars settle out, so we have the soil on the bottom, clear water on top, we'll find that the 30% residue cover will have only about half the soil compared to the bare plot. And that's why a lot of our conservation compliance plans that producers signed had residue cover in their plan. They wanted to keep that 30% cover to cut erosion in half. Fairly obvious on the 100% cover, the more cover we leave out there, the less soil we lose. That water's a lot cleaner. And when it comes to water quality issues, anytime we can keep our soil in the field, we keep a lot of our ag chemicals in the field. A lot of the fertilizers we use, the ag pesticides we use, bond to soil particles. So if we can reduce runoff and reduce soil erosion, we're going to reduce how many of those ag chemicals are lost off-site as well. Now as typical, I'm not catching all of the runoff because it does come off rather erratic. But you'll notice that those jars without the cover are almost full at the same time. Even the 30% cover almost full at the same time. The grass here where we have the roots, the worm channels, far less runoff. In fact, when you see it dripping out the bottom of the plot, that it went straight into the soil rather than running off the plot. That's again the better infiltration we get with good soil structure, with the no-till, with permanent vegetation. Now as those jars are full, I'm going to go ahead and shut the water off. Okay, we just saw the raindrop impact causing soil particle detachment. That same energy of the raindrop, though, was melting that soil surface and actually forming a crust on the soil surface. Without the residue here absorb that energy, I can reach down and I can actually pick up and get the crust to break off. A lot of people think a crust forms when the sun comes out and bakes it hard. No, the crust was formed right now during the rainstorm event, and it's about a 1/4 inch thick. It's a seal on top of that soil surface, and it flakes off there rather easily. And that seal on top then reduces how much water can soak in. And that's why we had quite a bit of runoff off of this plot. Now when I actually take a look at this, in the rain gauge, we are just over 1 inch of water applied. So that was a quick rainstorm event. We have a lot of producers out there in the middle of the summer who would wish for an inch of rain so it'd come help their crops out. But if we don't have a soil surface that will accept the water, a lot of it happens to occur as runoff. Now with that runoff though, we got the crust on top, we had more runoff. And that 1 inch of rain then, how far did it soak in? A greenhouse flat here is only about 2 inches deep. As I turn this over, we find dry soil in the bottom. That 1 inch of rain didn't even soak in. In fact, as I pull the dry soil away, it only soaked in about ½ inch deep. A 2 inch deep greenhouse flat has dry soil underneath. Because on a sloping soil, without something to reduce the crusting, without something to reduce raindrop impact, we have a lot of erosion and runoff because of that problem. Now, if we leave even a little bit of residue cover on the field, a 30% residue cover, we absorb some of the raindrop impact. When it comes to water soaking in, yeah, we had a little bit of water soak in, but it's about the same as with no residue cover. We still had some raindrop impact, still had some sealing, still had quite a bit of runoff and erosion. Now the last one, a lot clearer runoff, a little bit less volume there. In fact, these two jars overtopped. That third one with the residue cover did not. In fact, when I pull the residue away, we don't see the crust on top as I go to pick off the soil. So when I take the exact same soil, remember the only difference between these three plots was the residue cover on top. I turn this one over. We definitely see greater infiltration. We can definitely see how that residue now let that 1 inch of rain soak in all the way through. Far more water available to the crop than here, and even less water available here. So zero cover, the 30% cover, the 90 to 100% cover. Remember, these were all the same soil poured in loose into those greenhouse flats. So we are not doing anything special there other than protecting it from raindrop impact. The residue cover does a lot for us. The next one here is the no-till soil. We see some soil pads, some soil aggregates holding together. And as such, yes, there's a mild crust there, but it's not near as dense. As such, more water soaked in. And when I turn this one over to see how much infiltrated, again, wet all the way to the bottom. This is no residue cover, but it had good soil pads, good soil aggregates. We can actually see the soil particles still holding together there. Compared to this one, where there was no residue as well, there's no soil aggregation to hold those soil particles together. So again, the difference here was soil structure because of continuous no-till, no tillage, good biological life. This one's been tilled, breaking up the biological life, breaking up the soil structure. The water can't soak in as much. So again, we get better infiltration when we get that long-term no-till. And the final one, won't be much to see here because we have a permanent grass sod. It too is wet clear to the bottom, but it's also bound together with those roots. As I say, that sod is there holding the soil particles together. We see the roots here as well. Again, that is the soil structure that no-till gives us. And as we start thinking about tilled soils, we think about soil structure. Think about after the rainstorm event. You might be back on the back 40 of the farm. You're working on a tilled field. You get a heavy rain. And let's go back to this one. You can see there's not much there for soil structure to support us as we drive back into the farmstead. If we get something like this though, good soil structure, we can drive on that. It's a firm soil. That soil aggregation gives us structure such that the soil is more stable. It doesn't wash away. Far less runoff in the jar because the water soaked in. And now that same inch of rain that we received here didn't soak in, it ran off. With the no-till soil structure, we have that inch of rain available for our crops to use. Okay, the rainfall simulator ran just a little bit ago. We've given it a little time for the soil to settle in these jars. Now, ideally, when we do research on something like this, we take one of these jars, and this happens to be the jar from the no residue cover. We can see soil settling out here in the bottom. It's already about 1/2 to 3/4 inch deposition at the bottom of that jar. And as we look at that jar, then we can see the soil, we can see the water on top. Now for research, we'd let this set overnight or longer, such that all the soil settles out. Carefully weigh the jar, pour off the water, oven dry the soil, weigh the soil alone, then we can calculate how much soil was lost. And as we said, here on this no cover, there's already about 3/4 inch of soil on the bottom of that jar. When we go over to the 30% cover, 30% cover didn't look like much for cover, but when we look at the soil in the jar, there's less than a 1/2 inch. Again, a 30% residue cover on that jar will cut erosion in half compared to no cover at all on the field. And that's why our conservation compliance plans had that 30% cover, so we get a lot less soil particles detached. Coming over to the 100% cover, that jar has just a very thin layer of soil on the bottom. Now I should say it's actually about 95% cover, because looking straight down as a raindrop would see it, there was a little bit of bare soil there for raindrops to hit, but also that flowing water going across the soil surface can detach some soil particles. Now as we come over to the jar that was from the no-till soil, had soil aggregates there. There was unprotected from raindrop impact, so we still detached quite a few soil particles. We had some runoff here, but it's less soil loss compared to the no cover on the tilled soil. Let's say there's less than a 1/2 inch in this one as well. So again, that no-till soil structure, even without residue cover, cut erosion in about half. So that structure was worth a lot there for us. Better yet though, if we are a no-tiller, we are going to have residue cover out there. We're going to have root channels out there. We're going to have wormholes out there. We're going to let that water infiltrate. We're going to keep that soil attached. And this, from that sod covered one then, would be the no-till system with cover crops, for instance. A permanent cropping type of system. Very little runoff, very little soil loss coming off that jar there. So again, as we see, as we look across the jars, there's definitely a difference in the color of the runoff and how much sediment came off. And when we think about off-site pollution, we think about our runoff, we think about the ag chemicals that are moving. We want to keep the soil in place. We're going to reduce that movement. We want to get the water to soak in so it doesn't run off. Okay, got another little demonstration here to talk a little bit more about aggregate stability. With the rainfall seminar, we just saw how no-till soil, the soil particles held together such that the water could soak in between the soil particles, where the tilled soil just sort of melded together and made a crust on top. What I've got here is two soil clods. They look very similar. Well, they should be. They are similar soil. They're actually from about 50 feet apart in a field out here where we've had no-till since 1981. One clod. The other clod is from a field that's been plowed since 1981. I say the soils look the same, the clods look the same. Okay, these two clods, again, one is from no-till, one is from tilled. I'm going to just drop them into water. We'll see how water stable the aggregates are. The no-till soil, the soil beds are being held together by the natural glues from soil bacteria, from soil mycorrhiza, from everything that's holding soil particles together. The tilled one has less that soil biological life. So as we start looking at them, we see a little bit of sloughing off on the one, a little bit on the other. But the longer we wait, if we think about a rainstorm coming continuous, or we think about traffic on the soil, we start seeing differences. One breaks apart readily, has no soil structure holding them together. The other holds together much more compact. We stir the soil, or stir the water a little bit. Gets cloudy, the soil particles going in suspension. This one, stir it, a little bit of cloudy, but a lot clearer water because the soil particles are being held together because of that soil biological life. The no-till soil here has that biological life. Now this is from a cropped system, and that crop system, though we only have crops growing there about 5 months a year. We could do better if we had cover crops or permanent vegetative cover. But again, when we start looking at the clarity of the runoff from both of these, this would be a dirtier runoff from the tilled soil. We have more washing off. The no-till soil holds together much nicer. Again, when we look at the soil structure, the tilled one just sort of melts apart, and the no-till one is holding together somewhat. But I want to do a little bigger demonstration that will show that. And I have the same tilled and no-till soils here, but I've got them in sink strainers. And again, when we look at the two soils there, they look about the same. We got, again, the tilled soil and the no-till soil. And again, this is the same tillage system since 1981. And since here we are in 2008, that is now 28 years of tillage. And I got those wet by putting them down in that custard cup full of water, but I want to make sure they're wet clear to the top. So I'm going to pour water on top of them both. And I'm going to do a little demonstration of what we call wet aggregate stability. Again, they were crumbly soils in those strainers, just sort of poured in there. As such, you would think, well, they're loose soil. I'm going to pick them up a couple of times and let them drain, and just make sure the water gets between all the soil particles. Again, when it comes to wet aggregate stability, the soil biological life of the no-till, those soil particles hold together. The tilled ones will tend to melt apart a little bit. We see a minor difference in the runoff, but the major difference we'll see is when I dump the samples here. Turning both strainers over, and as we look at the soil particles, as we look at the mud pies, I like to call it, we look at the aggregate stability. And when I do youth programming, I like to talk about two technical terms. This one's more like chocolate pudding. You notice it just glistens. There's nothing there holding the soil particles together. Again, think about driving across a tilled field after a rain. Just sink in. It's just a mush. Compare it to this one. It's more like a chocolate brownie. I push on one side, it holds together. The soil particles are holding together. As I drive on it, yes, I can mush it down, but it's a far firmer soil. Those soil particles are holding together. Aggregate stability is there. Compared to the tilled one, there is no aggregate stability. And so again, we start thinking about biological life providing the glues to hold those soil particles together. There's glomalin, there's all sorts of microorganisms in the soils, but it's the soil particles that hold the particles together, and it's because of that I like the no-till system. As tillage, as we come in and do it, we break up the soil structure and we kill some of that soil biological life. We can improve that biological life by having a cover crop growing out there, by putting manure out there, by having more things to feed those soil microbes year-round. Not just those 5 months of the year that we have a crop growing out there. Again, these are from a cropping situation, so these are only fed for those 4, 5, 6 months a year, not year-round. We get to a native prairie, a pasture situation, we'll see better soil structure, better soil aggregates. So again, let's build that soil structure, get that biological life going in your soil.